Any questions?
Mitchell, I argued that the frequencies couldn't diffuse in the Flesch-Pons experiment, so they were co-deposited. In your experiments, because you've got this spiral, in the PHUSOR experience, because you've got this tight spiral, I'm kind of the opinion that that actually helps the local vacancy information. You probably don't need a style loading to make your vacancies in those PHUSOR experiments.
Could be. There's obviously, you were teaching last year that they diffused in.
No, it's for years. The numbers have always been the same. The diffusion coefficient is very small.
Very small.
They can't move near room temperature.
Okay. There's a lot of things we have to resolve is what's going on. Let's look at some excess energy in cold fusion systems. We've seen our definitions. We've seen that we've got to do thermal waveform reconstruction to make sure we believe it. We use redundant calibration. And now let's look at some outputs. This is a cold fusion PHUSOR just looking at temperature as a function of time. This is hours. So that's pretty bad. But this is over about 2 days. And so what we're looking at here is this is a water control, T3. And what we're looking at is the red line is our power in. So for the same amount of power in, which is over here, this is our control. We're getting a lower temperature. We're getting about 45 degrees or so, 46 degrees, versus here, where we're getting closer to 70. Okay? Degrees centigrade. We clearly see a difference between the two. And it turns out that because of contamination, in some of our systems, we only put the temperature detectors on the outside. For example, this one. So outside the container, where we're running the cold fusion system, we hit a temperature of 120 degrees centigrade. We know that we hit at least 160 inside because we melted the system. So for those who think you can't make your cup of tea, we have enough temperature to make a cup of tea. Here's a PHUSOR type system where we're using nickel as the cathode, ordinary water as the solution, and gold as the anode. And here over 35 hours is our result. We'll show you what it is. And we're looking up to 10 watts. So here, for example, in our Ohmic control, we would do noise measurement here. In our Ohmic control, we're putting in approximately 4 watts input power here, and we get a nice match out. On the cold fusion device, here's what we put in. We get more out. Again, this is a log curve. This is nickel with ordinary water, not the palladium and the heavy water. And here's our energy. So here we see a nice linear match, which is what we always see with the Ohmic control systems. And here we see a divergence, which is what we always see with the cold fusion systems. And here again it comes back to the noise when it turns off. Now the reason we're doing different levels is we're measuring the optimal operating points. Yes?
Essentially, you have these wonderful plots showing when things work. I need to twist your arm. You have a version of that plot for a dead cat that was dead as a doornail.
It's coming.
Power balance between in and out, so we can see an example of that.
It's coming. You know it's coming though. All right, here is with platinum as the anode, ordinary water in between, and a nickel PHUSOR. And here's our noise measurement. Here is the input to the Ohmic control. We get a little bit out less than we're putting in here. Here is the nickel cathode. We're getting more out than we put in on the log plot. Here we do the Ohmic control because we're putting so much into here we want to match it. So we do 2 more of the Ohmic control. We get a little less out than we put in. We go back to the nickel cathode, and voila, we're getting more out than we put in again. Okay? And we see that with energy too. When, well, you can't see the linear region here. The important point is, we do a control, aroma control. When we look at input power between here's 1.5 inputs to 2.5 watts up to 35 degrees, we're looking at delta T. How much does the temperature rise compared to where it was at the beginning? All right, we start with two identical volumes of water. This one is whatever it is, say 20 degrees centigrade. Now we're going to rise this to 40, either by the Ohmic control or the cold fusion device. That's a 20-degree difference. So that's what we're plotting here, delta T. It's not the temperature, it's the difference in temperature between doing nothing and driving it. And so here, for example, at 1.9's input, the Ohmic control, the reason that it goes here, it takes a little while to get up to equilibrium. But here we're seeing more out than we put in. So in terms, if this was your water heater in your cellar, you would be saving money, because this is what you pay now, and the ratio that you would pay, you would put the ratio in the denominator, and you would have that much savings. Here, for example, is another one where we're looking at the palladium PHUSOR with heavy water. So we use palladium as the cathode, platinum as the anode. Here's our Ohmic controls, and here's the PHUSOR in 5 different regions. And everywhere we look at it, we're getting more out than the Ohmic control. Again, this is input power now. This is not time. We're looking between about 1 and 7 watts input power. And we're seeing a delta T of 85 degrees. That was just below boiling. The other one must have been around 17 degrees. Delta T. We're not looking at the temperature, we're looking at the difference in temperature of how much we've risen the system. And again, I feel uncomfortable going above 100 degrees just because I don't like burning off $3,000 a liter material. Yeah?
Palladium is expensive, nickel is cheap, heavy water is expensive, light water is cheap. Does the palladium heavy water system have any advantages over nickel and light?
We're going to come to that. It does. It does. And but we will come to that. So let me show you a PHUSOR. In fact, I can even show you a picture of it if we're lucky. All right, what we're looking at here is the cathode, which is going to be wound over here, and the anode would be over on that wall. So the electric field intensity points from the anode to the cathode, and we showed this back in 2003 at ICCF 14 when I said to people that we see excess energy when we get the bubbles on one side, and the moderator pointed out, no, bubbles occur always on both sides. And fortunately, I had this video to show, which showed that we're getting bubbles on one side. And under these conditions is when we get the excess heat. And as I'll show you later, if it deteriorates where we get a gout of bubbles everywhere, we lose the excess heat. I'll show you that later. What we're doing with this, when we get to the section on metamaterials, is we are creating a flow within the palladium. So the electric field intensity is moving the deuterons to the cathode, creating a cathode fall. That's an exponential rise of the deuteron population right over here. And the electric field intensity then drives this into the metal. And they come, and this actually is our loss. When we get to the equations, you'll see that when we have a deuteron flux, it can do two things. It can either enter the metal or it can go up as gas. And yes?
That's what, in the bubbles, would that be some deuterium? Would that be oxygen?
That's deuterium. There is no oxygen at the cathode. Good question. Okay, let me go back to here. Nope. I guess I have to. Good. Okay, so here's our PHUSOR, and you know when you look at it, there's an anode that we're not showing way downstream. And this is a close-up that shows that it's active because we see the bubbling on one side, which you've now seen the time domain. And this actually gave rise to this curve. which is what we showed at ICCF 10. Okay. This is an optimal operating point. And what this means is we're looking at input power is here. This is between 0 and 8 watts. And this is our excess power we're looking at now in the vertical axis. This is how much power we're getting out beyond what we put in based on that temperature rise. And what we find is, here's our Ohmic control, so we get out just what we put in. They're at the 0 line. This is 100% efficiency here. Anything above is greater than 100% efficiency, okay? This is, everything up here is excess energy, but not all excess energies are alike. It turns out if we drive over here, we're getting less. Over here, all of a sudden we hit a peak and then it comes down. We believe that the reason there are different regions here is we believe this is insufficient loading and drive. Here we're having our peak, and beyond here we're getting wasteful electrolysis. I believe that when the bubbles form, we are actually not permanently damaging the system like a crack, but partially handicapping the system by cooling it, by removing the material we want to load and to flow through it. So we try to minimize the bubbling. So that's here at this is what we call the optimal operating point. We have to thank Peter Hagelstein for naming it, because I gave it a really dumb name and I won't even tell you what it is.
What are the actual voltages and currents?
Good question. Typically, we will drive our systems at tens to hundreds of volts, and we will drive at a fraction of a milliamp here if we can. And that's quite different from other people in the field who will drive from probably between 2 and 10 volts at high currents.
Is there some reason you don't use a chemical control using an inactive metal
We
rather
do.
than an ohmic control?
We do
Oh, you
with
do?
metals.
Okay.
The thing that we do different is we don't salt the solution. Okay? So when we get to the section on metamaterials, you'll see that the impedance of our solution, two-terminal impedance, will be up to half a megohm. And most people in the field, they're much less than that because they end up salting the solution. To us, that's the wrong way to go because that causes more bubbling and we never see the excess heat. In fact, we did experiments back in the early 90s that as we salted a whole number of materials and we always lost the excess heat. So we have found what we think is a much better way to do it. Here, for example, again, the proof's in the pudding. So this was a typical run that we have. Here's our time between 1 and 4,000 minutes. I'm sorry you can't read it. Here's our input power and output powers between 0 and 9 watts. And here's our energies, which is the time integral of these power curves. And the energies here goes between 0 and 900,000 joules. That's a lot of energy. And so, for example, here's our control. The red is the input power, and the blue is our observed output power from the control. Nice match. Less a match over here. So here we do the control, but it takes longer to heat up, so it doesn't come out as fast. And we're not as efficient at collecting it all when we put more in. It's not a perfect system. So we see that we're missing some of it over here, but here it's a pretty good match. And look at the PHUSOR. Here's our input to the PHUSOR, and we get much more out. And here we're looking for the optimal operating point, and we still get much more out. And here we're looking at 3 levels and multiple levels for the OOP that we're measuring, and more out for each of them. Okay? And again, if you could look closely, you would see that these regions are linear. Linear rise for both, and here it's superlinear. Questions? Okay. Keep losing control of this. Okay, here's another one where now we're looking at this also is a palladium PHUSOR with platinum as the anode. This is a log plot, And again, what we see with the controls, we get a nice match, input and output, and linear both here. And yet over here, we're seeing more out than we put in, over and over. We see a superlinear rise. Keep this down here, I guess. You saw this before. This is the dual ohmic calorimetry that we did. We don't do it this way anymore. By the way, over here, it's a little endothermic loading. This stuff is so accurate now that we're actually able not only to measure the heat after death, as well as the TARDIVE thermal power, which is heat after death is the integral of the TARDIVE means it comes on late. So we're seeing a thermal power after we drive it, and when we do the time integral, that is the heat after death. But we can also measure the loading over here, so we can measure that as well. And this was the demo where we're outside of Peter's office in 2003, where we were getting excess energies between 230% and 290% for the 5 days that we ran it. And one of the things we tried to show on Tuesday, which is when we invited everybody over, was the optimal operating points. And what we did is when initially we drove it at 8 a.m., we got 240%. As I showed you, we can go up and then bring it down, and here we did. And so we were able to show, in fact, that compared to the control, we got more out. And in fact, over the week, we even got the complete manifold. We call this the optimal operating point manifold. And here's the OOP where we like to drive it. This was a run that occurred, the open demo was 2003. Gene Malev, on the week that he was murdered, set up Popular Mechanics to come to watch the setup. We thought that would change the outlook of the world to cold fusion. So this was the run that we set up. And this was the run during which Gene was murdered, right about here. And here we see the ohmic control input and output. Here we see the input to the cold fusion device. And here we see the output. And so the excess energy is here. And these two are just such a sweet match, you can't even measure the difference. After Gene was killed, we put off having Popular Mechanics come, and we were graced by having Brian Josephson come, who couldn't quite believe that cold fusion was real, but he came out and saw it for himself. And this was the run where we actually took the device that had been at MIT, and for the first time we actually tried to refill the heavy water. So that's what it's taught here, is first ever refilling of cell 8. And we had been running it over months and months. And this was the run with Brian Josephson that got him to realize that in fact cold fusion was real. So here we see the ohmic control input and output are a match. Here's the input and output by power. Here's the input and output by energy. Again, if this was a perfect system, I often try to put this right between the two, which is what Lou Smullen taught me. But it's real hard to do it all. And so you'll see that some of them are perfect like that, but most of them are not quite that good. And in the run where he was there, this is our input to the PHUSOR with the refill. Here's our output. And again, it was great to have Brian there for that. And in fact, this was our power gain during that run. Now what's interesting is, he was wicked excited. He had never seen excess energy. And we were getting out 160% more than we were putting in. I was depressed because we were down from 290%. But it turns out the endorphin depends what you're used to. So here, the important point is, here is an optimal operating point manifold, even though we're only picking a part of it. Okay?
Could you please clarify when you say refill, that means your heavy water was all electrolyzed and you have to add?
I was concerned that over time, the impedance of the solution falls. I like high impedance. And it had come down to about 10,000 ohms, and I wanted it back up at 500,000, so I refilled it, hoping that would do
So
it.
you didn't really flush it, you just added water, correct?
No, I took it out and refilled it. I didn't just top it off.
Okay.
I had hoped that I could actually bring it up. But with our PHUSORs, contamination is a big issue. And it's not just, I mean, there's a whole story about that too.
Okay.
But darn good question. Let me just quickly summarize here before we go on to some engineering. These are results of excess energy observed with palladium and heavy water. We have gotten peak excess power out to 19 watts that we've reported. We've actually gotten higher, but it's the 19 watts where we have really tight semi-quantitative calibration that I'm willing to put my head in the chopping block on. And 19 watts, as I'll show you, was enough where we were driving the Stirling engine so far, I thought they were going to fly off the desk. Our power gains here, anyway, you can read them off here. Recently, we've added the nanomaterials where we get energy gains up to 40. This is a dual anode PHUSOR where we got energy gain at 80, but only for a short amount of time. It melted the anode. This actually we've been able to keep going for months. So we're in a whole different field now with the nanomaterials. We'll come to that. These are our quick summary of our results with nickel light water systems. And again, we see good energy gain. 5. The reason we like the palladium deuterons now is we're getting energy gains of 20 to 40. And I don't see that with the nickel. And again, in terms of aluminum or damaged nickel, and we'll talk about damaged nickel, this is actually, Peter, you reported that actually at China at ICCF9 where we had the damaged cathode. We'll show that in a bit. Deuterons destroy the nickel and can actually make it just like an ohmic resistor, and I'll show you. And I think that's what Peter was referring to. And here we have aluminum and iron, and we don't get anything near excess energy, so we use those as chemical controls as well. Take-home points. We can get excess energy out of cold fusion. It is greater than the amount of energy that could be stored, and it is greater than the amount of energy contained in the materials. It is a fact. It can only have a nuclear origin because of its quantity, and in fact the measurements of commensurate helium-4 with the amount of excess energy and the rate of generation of helium-4 de novo with the excess power shows in fact that we know the substrate, deuterons, and we know the product, helium-4 in cold fusion. Questions?
I just wanted to check. Did you try to run it in reverse voltage and see what's happening?
Yes. We don't get it depends what you mean. What we tend to do is outgas. If you loaded it and then reverse the voltage, you outgas. We don't get excess energy from that. Yeah.
When you recharged that one device and removed the heavy water, did you analyze it to see what was going on to make the impedance drop the way you said it does?
Should have, didn't. Darn good question. We should run one of them just with that. One of the problems we have is lack of funding. Okay? If we had more funding, there is no limit to the amount of tests we could do for materials, and we need it. We're desperately in need. But right now it doesn't exist. The key to getting these things to work is deuteron flux. And flux is this, it's flow. And we believe that successful cold fusion requires deuteron flux, which is described by the quasi-one-dimensional model of loading. And again, I've got the papers here. People say that there's no theory in cold fusion. Peter gave you some theories that explain where cold fusion occurs and how. And the quasi-one-dimensional model has taught us a lot about how to drive these systems from an engineering point of view. It's taught us Yeah, we'll keep losing this. It's taught us about co-deposition. We were doing co-deposition back in 1989. It's taught us about how to load it. This is not working. Right. I apologize. The other important thing about loading is that it gives us a net. You need a certain amount of loading, as Peter showed last week, in order to get excess energy. You've got to get an atomic ratio of deuterons to palladium of at least 85, 86%. After that, you see this quadratic rise in excess energy. Now, let's analyze for a moment. It's MIT. We've got to have one equation, I guess, at least, of what's going on here. So we're going to talk about deuteron flow between the anode and the cathode, which is over here. And the flux of deuterons brings from the heavy water solution all of these deuterons in a cathode fall in front of the cathode. From there, we could have it enter the metal. I call it JE. We could have a very tiny amount go to fusion. It ain't very much because of we know that we're only making 10 to the 11th, 10 to the 12th per joule. So this is very tiny. And most of it goes up in gas, and we don't like that. And it turns out that there's an interstitial flow that we discovered with the metamaterials, and we'll come to that in a second. This is the flow equation. There's two terms. There's a diffusive term. This is from the gradient of the concentration. This is our diffusivity of the deuterons. So things will flow, the deuterons will flow down the concentration gradient. And this is from the electric field. This is the concentration. This is the electric field, the change of potential as a function of distance. And this is our electrophoretic mobility. So we analyze this equation. We take the equation, and what we find when we do it is that we can take the equation and create what's called the first order rate constant. We take these terms and divide them by the concentration. And it turns out, this is incredibly important because I believe this is for me, the first equation in cold fusion that says how to drive these devices. What it says is the first order rate of entry into the metal depends on the electric field and the electrophoretic mobility. That makes sense. After all, we're applying an electric field intensity, so the amount that's going to go in is how much we're driving towards the cathode, minus what goes up in the gas, and we can ignore that, it's a tiny number, minus what we use for fusion. And if we take these two equations, we find something really interesting. We're not going to get, remember, we're not getting excess energy unless we get a loading of at least 86%. We want more than 86% because we want that curve to come up. And therefore, this is a killer. This isn't much of a killer because we're not making that much, but this is a killer. And it turns out that minus sign, I believe, is the reason most people miss cold fusion, is they thought the gas was so exciting coming out. I mean, I went to laboratories in 1989, and we showed our first device that was making cold fusion. They didn't like it because it didn't make the bubbling. It didn't make the bubbling because it was putting it into the metal. Anyway, what we can do is take the we take the terms, and what we see here is that the entry depends on two terms. This is the diffusive constant, this is the applied voltage, electric charge, and this is thermal disruption, the Boltzmann constant times the temperature. So what we find is the ability for the deuterons to enter the metal depends on the ratio of two energies. It's the ratio at which we're forcing it in over the thermal disorientation of kT minus what we lose in the gas. Take-home point. Successful cold, if you can get something out of this section, if you want successful cold fusion, it is not electrolysis. And it's funny because everybody says it's fusion by electrolysis. Well, it's the one thing cold fusion is not. It's 1 minus electrolysis. Okay, optimal operating point engineering. What are these optimal operating points? I showed you one before for the palladium heavy water PHUSOR, and it turns out we see that it characterizes the high impedance systems in palladium, in nickel. It characterizes the original Fleischmann-Pons experiments. It characterizes tritium generation. The excess heat in the nanors. It even characterizes what I'll show you in our, we made transistors out of the nanors. So it turns out that in the overloading, we even see it there. Here again is one of these optimal operating point manifolds. Oh no. The optimal operating point reflects the narrow peak of, in the case of heat production, the generation of heat in helium-4. And if you drive beyond the optimal operating point, you're wasting the energy. You're going to lower the efficiency of your system. I believe that many negative results in cold fusion have been from the failure to understand this and from driving it at the wrong place. Let's look at some data. Here is tritium production from Spock with co-deposition. Here's tritium production from Spock without co-deposition. This is the heat production from palladium and heavy water. This is helium production from palladium and heavy water. And this is from nickel. And this is from nanomaterials, but we'll come to that in a second. Now, there's something I think really important here. Let's take a look at, first of all, these two overlap. And what's really interesting about them is they overlap. If you look, we're looking at input electrical power here between milliwatt and 100 watts input. And we're looking at output of various things. People say cold fusion is not reproducible. Not if you look at it along the input power axis. If you look at cold fusion along the input power axis, you find there are many regions where you get low output, that is, it doesn't work, but you find out the regions where it does work. And here you find that the helium production and the excess energy that you see are commensurate. You also find that there's maybe two different reactions that we can control. It may be that the tritium production is separate from the helium-4 production. Yes?
So, Mitchell, we talked about, last week we talked about something like this in terms of current density for Fleischmann-Pons cathodes. And we talked about 3 different regions. So the region of high current density above 250, 300 milliwatts or milliamps per square centimeter was where excess heat moved. One tritium number that I had available was around 70 milliamps per square centimeter. And what's not on your curve is the lower region where low level neutron and nuclear emissions occurs. And in terms of current density for Fleischmann-Pons class cathodes, that's in the neighborhood of 10 to about 30 milliamps per square centimeter. So it's very consistent.
It would be wonderful to add it. When I got these curves, Spock and Miles had only published the currents. And I had to ask them both go into their notebooks to get the voltages so I could do these curves. Because we had seen this for the nickel and for our palladium, and I was thinking, we got to see if it's true for the rest. So what we should do is add that. Maybe by next year we'll add the neutron material too. But I've not done that. I've only done these two. And Stan Spock and Mel Miles were wonderful. They went in their notebooks, they gave the data which had not been published, and that's where these curves come from. Now we can take these curves. What's really interesting is by doing many thousands of experiments with heavy water and palladium, we now have the actual form factor. I drew these as sort of Gaussians or something, but this is what it actually looks like. It's a slow rise up, hits the top, and comes down. We know the form factor now, but when I did the first curve, we didn't know it. And there may be one for neutrons. It's true. I think the important take-home part is here is that they exist and that they may be separate. And that, in fact, when you align up cold fusion results this way, all of a sudden, things that seem some work, some don't work, all of a sudden we have a curve where they all fit together. Now, one thing I want to show you here is that these optimal operating point manifolds grow over time. So, for example, here we take this one's with a PHUSOR too. In a little bit, I'll explain how we got to PHUSORs. We didn't start with them. It just turned out that when I tried hundreds of different cathodes, there was one kind that stuck out. And then we began using it, and I'll show you how and why. But what's interesting here is you see over time, here's our input power from 0 to 9 watts input. Here's our power gain from 1 to 2.6, so this is break even right here. And they grow over time. They move, they shift. So if you measure it, it may not characterize your device tomorrow. It may go up or down, depending how you treat the device. Ed Storms didn't believe, he still doesn't believe in optimal operating points, so I asked him to send me his data, and this is his data. And so even the skeptics' data shows that, in fact, we can see optimal operating points exist and that they change over time. Here, for example, is with co-deposition. We can see, in fact, this is input power from 0 to 12 watts input with co-deposition. And here's our excess power in watts from 0 to 3 watts. And we can see that with increase, I put this down as increased loading. In fact, it may be increased growth. I think as a result of some of the things that Peter's been teaching and we've been learning, it may be time to readjust these slides. I thought this was loading. It may be growth of the domain as well. We will resolve it over time. But the thing is, it changes. The thing is, these are dynamic, and that they also show where to drive these systems. People who claim you can just take a nickel isn't even a nickel anymore, but you go on the internet, they say, well, take a nickel, connect it to a battery. You're not going to get cold fusion with that, even if you use a real piece of nickel, because it's unlikely you'll find the center unless you look for it. Okay, here we've taken a nickel PHUSOR, and one of the things I discovered to my horror was, to my elation, I found if I doped the ordinary water with deuterium, probably the only experiment I know of where anybody's even looked at adding deuterium to ordinary water, we increased the excess energy coming out, and I'll show you those curves. But as we did it, we found that above a certain level of drive and a certain level of loading or alloying, whatever term you want to use for that material, when the deuterium is in the nickel changed color, it changed electrical resistance, it changed its properties, and to my horror, it became totally inactive. And so this was as dead as a doornail. I'll show you pictures later where it changes from looking silvery nickelish to looking black and no longer work. This is our inactive nickel electrode. And so here, for example, here's our, what we're looking is a heavy water boost of 14% heavy water. We're getting to a power gain of 2. Here we overdid it. And we can see, in fact, that the conductivity of the nickel, normally 8.8 microohms centimeters, fell, and at that point we had an active, inert, dead cathode. One more thing, there may be 2 types of optimal operating points. Oopsie. We find when we drive motors that there's a functional second peak. I'm not quite sure what it means yet. So when we measure heat, we see this. When we try to do energy production, we see that, and I haven't deconvolved the whole thing yet. But the fact is these are not constant, either of them, and there's a lot of engineering here. As I showed you that we taught optimal operating points, let me jump ahead. This, in fact, is, we'll come to the motors. What we have is here is there's a cold fusion device under here. There's an Ohmic control under here. These are in electrical series. We're measuring, this was about half the power, or a third of the power going into this, and it's spinning around. This one, we're getting 3 times as much power in to the Ohmic control, and there's still not enough heat coming out even to turn it. And I'll show you this in a bit when we go back. And here's our optimal operating point. This is with 19 watts excess power coming out, but we hit the peak here at 5 watts input. And here we're getting twice of what we put in. Take-home message. Optimal operating point manifolds can explain a vast amount of data. Otherwise, where people say it's not reproducible. And yet when you put it in as a function of input power, they all line up. And what initially seemed incoherent now becomes clear. I believe